In the last video, we mentioned that data is moved between different levels of the memory hierarchy in blocks. This means that when the CPU brings a particular value into a register, if that causes data to be transferred between the RAM and the cache, more than just the single number that the CPU was requesting will be brought into the cache. The reason for this is that all of the storage technologies we have available have some sort of latency. This means that the time to access the first bit of data is longer than the amount of time to access subsequent bits of data once we have started reading or writing. For example, on a hard drive, the latency comes from the time that it takes to move the read-write head into position and rotate the disk to the beginning of the data that we are trying to read or write. But even for the technologies that underlie RAM and cache, there is some amount of latency before data starts being transferred. Because of this latency, it makes sense to transfer data in relatively large blocks. For example, once we have found the position on the disk where we want to start reading, it's easy to continue reading from that point and bring in a block of nearby data. And in addition to being easy to do, bringing in an entire block of data is often useful because we know that programs often exhibit spatial locality. In addition, because of temporal locality, when we have accessed some data that's in a lower level of the memory hierarchy, it makes sense to also bring that data into the higher levels of the memory hierarchy because that same data is likely to be accessed again soon. The result is that when our programs perform a memory operation, the data that our program is looking for will be found wherever it currently is in the memory hierarchy, and that data, along with the block that contains it, will be brought up the memory hierarchy into the cache. Then, if we, in the near future, access the same data again, or other data that's nearby, our subsequent memory accesses will find the data that they're looking for in the cache and be able to execute faster. Because our programs can execute significantly faster when the data that they're operating on is in the cache, it can be useful in reasoning about our programs to think about their cache hit rate, that is the fraction of their memory accesses that will find the data they're looking for in cache, or equivalently to think about their cache miss rate, that is the fraction of memory accesses that will have to go lower down the memory hierarchy because the data wasn't in the cache. This is particularly important if we are traversing a large array, because the way that we index into an array can make a big difference in the miss rate. In this snippet of C code, we have two two-dimensional arrays, A and B. Both are dynamically allocated and live in the heap segment, but A is the array of arrays style of allocation, whereas B is the single allocation style. And for this double for loop that traverses both arrays, we can think about the blocks that are being brought into the cache, and therefore the miss rates that will happen for different styles in which we could traverse each of the arrays. When we begin executing these loops with both indices equal to 0, if this is the first time we've accessed data in these arrays, or the first time in a while, then there will be a cache miss, and we will have to bring in the first element of each array. When we execute this line, we will be accessing first an index into the outer array, and with r equal to 0, we will access this location. This will be a cache miss, and so we will have to bring in the data that we are accessing, and along with that data will come the block that contains it. So we will get not just this entry in the array, but in fact the next few entries in the array. How many entries come along as a part of that block depends on the size of blocks that our system moves between the RAM and the cache, and on the size of the data type that we are accessing. If A is an array of integers allocated in the array of arrays style, then the data type of this value is int pointer. On most modern systems, if we were to evaluate size of int star, we would get 8, because on a 64-bit system, pointers take 64 bits to store, and addresses are measured in terms of number of bytes, where a byte is 8 bits. And so a 64-bit pointer takes up 8 bytes. We also need to know the size of a block, and that is something that depends on the specific architecture of the system that we are working with. Different CPUs might use different block sizes when they move data between the RAM and the cache, or between levels of the cache. But for now, let's assume that this system that we're working with has 128 bytes as its block size. So that means that every time we have a cache miss and have to go get the data from the RAM, we will bring 128 bytes of data from the RAM into the cache. And so if an int pointer takes up 8 bytes, and there are 128 bytes in each block, then every time we bring in a block, that can hold 16 int pointer values. And so the first time that we have a cache miss, we will bring in both the pointer that we were accessing and the next 15 pointers. So we had a cache miss for accessing the outer array, but once we have found the pointer value in the block that we brought in, we'll now have another cache miss when we access element 0 of the inner array. And so here, when we try to access this element, we will again be retrieving from the cache an entire block of data. On most systems, int refers to a 32-bit integer value, and so size of int should be 4 bytes, which means that we can fit 32 integers into a 128-byte block. So we will have a miss for the column index as well, but when we bring that particular integer into the cache, we will also get the next 31 integers worth of data along with it. So now, if we think about how does this line perform over the course of executing this double for loop, well, on the next iteration of the inner loop, r will still be 0 and c will now be 1. So when we access index r, we will be accessing a pointer that is already in the cache, and then we will be accessing an integer that is right next to the one we've already accessed. And so that will also have been brought into the cache on our previous miss. So on the next iteration of this inner loop, we will have a cache hit. And in fact, for the next 31 iterations of this inner loop, this line will have cache hits for both indices. It's only when we get to a C value of 32 that we will cross out of the block of integers that we brought in and have another cache miss where we will have to retrieve another block from lower in the memory hierarchy. And so over the course of one iteration of the outer loop, this line will have a miss rate on average of 1/32 of the time. If we look at our array B, we will, on the first iteration, be accessing element 0 of the single allocation array. And again, this will be a cache miss, but when we bring in that integer, we will get with it 32 integers worth of data. And then our next 31 accesses into this array of integers will be cache hits. And so over the course of one iteration of the outer loop, we will again have that a 1 over 32 fraction of the accesses into the B array will be cache misses. At the start of the next iteration of the outer loop, we will advance to the next pointer in our array of arrays. And since we have been frequently accessing this block that we brought in that contained the first 16 pointers of the array of arrays, we should find ourselves having a cache hit in the outer array on the first iteration, and then a cache miss on the inner array, and then we will get similar behavior on the inner loop. For the B array, we might or might not have a miss on the very first iteration. That will depend on how the block size and the width of our array align. But this is why we think about these as an overall rate, rather than trying to count exactly the number of misses, that on average we will have 1 over 32 of our inner loop iterations having a miss, and we don't need to worry about whether or not the very first iteration is a miss, because as we continue looping through this second row, 1 in 32 of the accesses will go out the end of a block. So far, these approaches have seemed fairly similar, and we have been taking good advantage of spatial locality to get a relatively low miss rate. But let's think about what would happen if we changed the way that we were indexing into our arrays. If we switch the indices of our for loops so that our outer loop is now over the columns and our inner loop is over the rows, on the first iteration, it will still be the case, if we haven't accessed the arrays recently, that accessing index 0, 0 of the array of arrays will cause 2 cache misses. One for the array of pointers, and one for the inner array. And the blocks of data that will be brought in will be the same, but on the next iteration, if we have incremented R and C is still 0, then the thing that we will be accessing will be this position in the outer array, and then this position in the inner array. And so we'll have a hit in the outer array because we brought in 16 pointers in a block, but then we'll have a miss in the inner array because the block that we brought in was from the first of the inner arrays, and now we're accessing something that is in a completely different inner array, and so isn't going to be in the same block. And as we proceed, every time we access a new row, we are going to have a miss in the inner array. And as we proceed down through our rows, we will eventually go out of the pointer block that we brought in. And so on the 17th access, we will also have a miss in the outer array. And so for the version of our loops where the columns are the outer index, this version of the array will have a miss for every access to the inner arrays, and it will have a miss 1/16 of the time in the outer array. So for every 16 iterations of the inner loop, we will have 17 cache misses from this line. If we think about the B array, we will again be accessing this element, and we will again bring in a block of contiguous values. But now as we iterate R, we are not going to the next index in the block, but rather we are jumping ahead by m indices in the block. And so if m is at least 32, then every time that we jump ahead, we will be leaving the block that we just brought in. And even if m were less than 32, we would be increasing our miss rate because we would be skipping over indices and leaving the block sooner. So let's assume here that m is at least 32, which would mean that every single time that we go to the next row, we are going to have a cache miss. Which gives us a miss rate of 1. We will have a single cache miss for the line that accesses B on every iteration of this inner loop. We could, in principle, also think about what sort of locality are we getting in terms of the outer loop here. But for things that we accessed on previous iterations of the outer loop to still be in the cache, it must be the case that the total amount of data that we brought in while iterating through the inner loop was not enough to fill up the cache, and therefore the things that we brought in a long time ago and haven't been using could still be in the cache. So if the dimensions of our array m and n are very large, then we can ignore the outer loop in terms of calculating our miss rates. But if m and n are small, then we might need to think about how big is the cache, or the level of cache that we are analyzing, and then how many blocks of data would need to be brought in before we've filled up the cache and have to start kicking out some of the older data. And so in the next lecture, we'll start thinking about cache replacement, where we'll need to decide and keep track of what data gets to stay in the cache.